we have two groups, the group consisting of the integers together with addition, and the group consisting of the remainders upon division by 2 together with addition modulo 2. Addition modulo 2 is defined by the Cayley table. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0. Under normal addition, 1 plus 1 is 2. But upon division by 2, the remainder is 0. That's how addition modulo 2 works. Now, is there a relationship between these two groups? Well, they are not isomorphic because the group consisting of integers together with addition is an infinite group, but our second group is not. However, there is a relationship, and it relates to parity. When we have two integers and we add them, if both integers are even, the answer is even. If both integers are odd, the answer is even. When the two integers have different parity, one even, the other one odd, when we add them, we get an odd integer. Now, that same thing happens in our second group. In Z2, there is an even and there is an odd. The even being 0, the odd being 1. Observe, when we add even plus even, we get even. When we add odd plus odd, we get even. When we add an even and an odd, or an odd and an even, we get an odd answer. Now, let's define a rule between these two sets, the set of integers and the set of remainders upon division by 2. Now let's call it f. That rule, f, takes z into z2 and is defined by f of x equals 0 if x is even, 1 if x is odd. Now, let's add two integers and apply f to the result. So here I'm going to have my first integer is going to be x, my second integer is going to be y. Now there are two cases of x, even, odd. So x could be even or it could be odd. Similarly for y, y could be even or it could be odd. Now we know the result. Even plus even is even. Even plus odd is odd. Odd plus even is odd. Odd plus odd is even. Now each of these are cases of x plus y. So this is a case of x plus y. That's another case of x plus y. And so on. Now, what I want is to apply f to the result. What is f of x plus y in this case? Well, it's f of even. F of an even according to our rule, is going to be 0. Now, this other case, I'm applying f to f. I am applying f to x plus y, where the result x plus y is odd. So I know the result f of odd is 1 because of our definition of f, and so on. Now let's observe that our results of applying f to x plus y has yielded the outcomes of our Cayley table for addition modulo 2 of Z2. But let's also observe even further. Now, this is a case of f of y. So when y is an even, f of y is 0. When y is an odd number, f of y is 1, and so on. Here we have x, so f of x when x is even gives 0, and if x is odd, f of x is 1. So now we can see that not only are the results matching our Cayley table, but also what we inputted. If we apply f to that, in each case, we get exactly the same inputs as those of the Cayley table for addition modulo 2 in Z2. What is the conclusion from this? The conclusion from this observation is that it is always the case that for every pair of integers x and y, so for x of y in the set of integers, we are getting the following. When we evaluate f at x plus y, here the addition is in the set of integers, the result is the same as if we apply f to x and then add modulo 2 f of y. So we have been able to connect parity by means of this particular function. It is a function, and it happens to preserve the operation addition of integers. So this is an example of what we call in algebra of a homomorphism. So f is an example of a homomorphism between these two groups. Now what we want to do next is define the condition of two groups being homomorphic in general, which is going to go as follows. We have two groups, two generic groups, G1 star and G2 dot. So let G1 star and G2 dot be groups. A function f from G1 into G2 is a group homomorphism between G1 and G2 if and only if f of x star y equals to f of x dot f of y for all xy in G1. That's what happened in our example. We had a function from the set of the first group into the set of the second group. And that function preserved the operation of the first group. More. Groups G1 star and G2 dot are homomorphic if there is some group homomorphism between them. When the two groups are homomorphic, we denote it by the notation of homomorphism. So when G1 star and G2 dot are two homomorphic groups, we denote it by group G1 star is homomorphic to group G2 dot. Or succinctly, G1 is homomorphic to G2. So in our case, the group Z together with addition is homomorphic to the group Z2 together with addition modulo 2. That's all.